Wondering if you could record.
Awesome. Thank you so much for the reminder. I really appreciate how y'all look out for other folks in your class. So let's see. So right before lunch, we were talking about this box plot comparing spending scores between non-males and males. And so we had enough of a difference that there might be something there, but let's run a t-test. So we're running a two-tailed, two-sample t-test. Two tails because we don't care about the direction, two samples because we care about comparing two populations of the overall. Something brand new that I introduced right before lunch. Oh my God, brand new stuff, freak out. Is this thing called Levene's test. And Levene's test is, if you can imagine, it's a statistical test, and it will, the null hypothesis of Levene's test is that the variances between two populations are the same. That's our null hypothesis. So rather than just randomly assuming things or guessing, we can run a test. And if we have evidence that supports that claim or refutes that claim, okay? So pulling in the non-male spending score and the male spending score, that gives us two different series. And stats.levene takes in those two series. The null hypothesis on a Levene's test is that the variances of both populations are the same. We fail to reject the null hypothesis. This tells us that the evidence does not support the claim that the variances are different. So, ergo, when we run our t-test for independence, we send in the non-male spending score, the male spending score, and the third argument is equal variance. We set that to true because our t-test, we failed to reject the null hypothesis from that Levene's test. And what do we get back from our t-test for independence? Well, our t-test gives us back the t-statistic. It also gives us a p-value. And you know what? That p-value is just so dang high, we don't have enough information. We don't have enough evidence to support rejecting the null hypothesis that spending score is significantly different based on gender. It's a pretty high p-value. Right, that's very little evidence that supports rejecting it. So sometimes things might be visually convincing, but run a stats test to compare because that p-value tells you basically how much evidence for the null hypothesis you have. So let's keep on digging. There might be something going on because we do have different looking box and whisker plots, but this could be for other reasons, other variables, right? So let's keep on going, see what we can do. Okay. So let's investigate our relationship between spending score, that's that index up to 100, and annual income. And a scatter plot is going to be a wonderful way to show a relationship visually. If we have a straight line relationship, it leaps off the screen. If it's curvilinear, it leaps off the screen. If it's like a V, it leaps off the screen. So what do we have here? What we're doing right here with the Seaborn joint plot, a joint plot is a scatter plot that has a histogram for each one of the axes. That's all that we're looking at. So we have annual income by spending score, and then we see across the x-axis is this annual income distribution, and then across the y-axis is the spending score distribution. That's what the joint plot is giving us. I'd recommend keeping your joint plots to not to yourself, but to more technical audiences, right? It's a lot going on one chart for most folks. And if you need to make an argument that's subtle and based off the distribution, might not be the best place. But it's jumping off the screen. We don't seem to have a linear relationship. Do y'all see anything in there? Yeah. It almost looks like the Purina dog chow brand, where it's like a checkerboard almost, right? Yeah. And so sometimes these things are going to leap out at you. we do need to finish writing down our takeaway for this one area, because there might be other variables that can explain this relationship, right? We have age, but it's not present on this chart. We have gender, but it's not present on this chart. So is there a linear positive relationship for males, a linear negative relationship for females? We don't know yet. Is there a linear positive relationship for young people and a downward sloping relationship for older folks? We still don't know yet. So we have established there's not a linear relationship, but it appears that there's an X in here. And at this point, the answer to your last question, much like a technical interview, your answer to the last question can be the question for the next question, right? The next question is, what is causing this? Maybe it's age, maybe it's gender. We already saw that gender didn't seem to play much of a role in the spending score. So let's see what's going on with age. So our next hypothesis, what is the relationship between age and spending score? So we're going to plot them out, ask if it's a linear relationship. If there appears to be something there, we can run a Spearman's test. And let's see what we have here. Between age and spending score, what are y'all seeing right here?
Is lower. At around 40.
Almost the spending score is higher, right?
Yeah, it's higher than a wider range. The older
Yeah.
it goes, like it drops off at a certain age.
Yeah. It's like one generation spending everything on another generation, maybe. That's my hypothesis. Who knows? But we no longer have that X. We no longer have that checkerboard, right? So this tells us, well, maybe there's something else going on. So what we're going to do in this example here is try to, there's something identifiable going on around the 40s, right? We no longer have those super high spending scores. They max out at 60, not even 60. So what if we were to make some bins, right? 0 through 40, 40 through 80, and see what we've got here. So the code where we make the bins is a pd.cut. The rationale for making bins is when you make bins, you lose the granularity of those single observations, but you might gain the clarity. Question?
Granularity.
Fine grainedness. Fine grainedness. So like you've had like coarse salt before, and then you've had like table salt. Table salt is more granular, more fine grained. So we're losing our fine grain. Thank you for seeking the clarity there. We're losing, like, either we lose the information that went into the bin, or when we look at the bin in isolation, we lose that information. But we get an idea of the boundary. Like if we have a boundary that's leaping off the screen at us, why not bin on that boundary that's leaping off the screen at us, so that we can understand it in an aggregate. And when we look at our aggregates here, why can we do a box plot for each? Well, because each is a category, right? So 0 through 40, that spending score median is like 64, 63. And folks 40 and under are spending quite a bit. The folks 40 and to 80 are spending considerably less. Their median, look at that. The median spending score for the 40 to 80 crowd is just a hair above the first quartile for the spending score of 0 to 40. It's like an MTV commercial or something, I don't know. So there's something here. Definitely a difference between those groups. We do want to be thorough, we could run a stats test here. I think this one is pretty visually cut and dry. Like if one population's first quartile is the same exact value as another population's median. But there is a bit of overlap here, so let's be thorough. We're running a Levine's test here to test the assumption of equal variance, and we reject the heck out of that null hypothesis. Do you need to know Levine personally to use the Levine test? No, you just drill in the numbers and get back to p-value, right? Your p-value from these two different populations tells you if it's lower than your alpha, it tells you that they have different variance. You have evidence to support rejecting them all. So our variances are unequal. What does this then allow us to do or force us to do? It means in the t-test for independence, we're going to say the equal variance is false. Really what's going to go on underneath the hood is when we have dissimilar variances, the test is going to be more strict. To get a lower p-value means it's got to jump through more hoops. So this p-value of 2.08 times 10 to the negative 6, that's quite a lot of zeros. So we find quite a bit of evidence to reject the null hypothesis that the spending scores for 0 to 40 are the same as 40 to 80. And that makes sense. That's what we're looking at, right? So now we can have more faith in the visual. Definitely something going on there. There's not a linear relationship. And this is why we just don't throw correlation at every damn thing. Because there's lots more types of relationships on planet Earth than just linear, right? Think about if you threw a linear correlation at, say, oh, I don't know, an absolute value function. It'd tell you that there's, what's the R? Z. If the R is 0 on an absolute value function, is there a relationship between X and Y on an absolute value? Yeah, you betcha. So always plot your stuff. So this tells us there's something going on with age. There's something going on with age and spending score. And this leads us into our next question. If we control for age, so we just proved that statistically and visually that age and spending score, there's something going on there, right? It's not so much linear so much as it is folks above 40 years of age don't have a spending score of greater than 60, right? So they're probably saving or spending for somebody else. So this next question has this very important language. If we control for age, does spending score differ across annual incomes? So you may notice the English here has 3 different variables, right? We have age, spending score, and annual income. So one way that we could control for age, we've already made 2 different bins for age. We could plot out income versus spending score for each of our age bins. And if the shape looks the same, then that means that age doesn't give any explanatory value. But if the plot between income and spending score looks different on any one of these bins, then that also supports the claim that maybe there's something going on, not just with spending score, but with income as well. So we'll analyze each of our bins separately. Remember, we made 2 bins. So this language of controlling for one variable means trying to figure out what the story is regardless of that variable you're trying to control for. So does that mean we're taking age into account? Yes. Does it mean that we will look at 40 and above and also look at 40 and below? Yes. So we plot all the things because now it's kind of hard to make 3-dimensional plots, even harder to really understand them. So let's take a look at the code. I'm going to make a happy little scatter plot here. X is annual income, Y is spending score. And this is for folks who are under 40. There's a couple of ways of controlling for variables like this. We could control for variables with subsets like we're doing here. You could also control for other categorical variables with things like the column argument or the hue argument. So if you use the column argument, say on a binary category, and you plot your X and your Y, and the X and your Y look the same regardless of the binary variable between them, like then that tells you that binary variable doesn't have much impact, right? So we don't have a strict linear relationship. We're kind of back to that X, back to that checkerboard for under 40. So what if we looked at above 40? Well, change the code a little bit. Annual income on the X, Y is the spending score. The data, the subset for the data that we're plotting is individuals who are aged less than 40. And lo and behold, we no longer have that X relationship or that checkerboard relationship between spending and income. We have the bottom half of it, it looks like. What does this seem to indicate?
Around 40 to 60,000 consistent spending budget.
Say that one more time.
The people around 40 to 60,000 for annual income. Relatively similar buying pattern in terms of price.
Say the first part again for me.
Annual income 40 to 60.
40 to 60. Oh yeah, this range right here. So you're talking about this kind of cluster. The individuals who are 40 to 60 all seem to have a very similar spending score. Yeah, that's correct. And where we saw in the data before, we didn't see many young folks with a high spending score. There's still some high earners, but they're not spending high. So they might be, those individuals might be saving instead of spending, or they spend somewhere else other than the mall. Question? Did you have a comment, Jen?
Oh, I just was gonna add something like, you might need to look at like different needs, like,
Yeah. Look, this part of breaking things into 40 and above really came from this first visual. But contained within inside of this one visual, there might be different brackets, different age ranges. Certainly marketers are not happy to have only two age ranges, right? Or only two kind of demographics. So we can make our own bins on our own values, and our values could be informed by social or cultural assumptions. Yeah. So what did we find about this? I did mention we could use either hue or subplots. Let's see. This kind of large age range of 0 to 40, what if we were to split this up a little farther? And we could look at people in their 30s and people not in their 30s. So another slicing and dicing. So this is really what we mean when we're slicing and dicing the data. We're comparing subgroups with other subgroups, with other populations, with the overall population. And what we find here, let's see what we've got. We have orange is the people in their 30s. So not a lot of high income earners. Just a couple. And purple is folks in their 30s. And I see a little bit more orange in the middle and on the left than the purple. And I see a bit more purple like in the upper right than in the upper left, for example. So these bins that you make where you try to control for a variable, make these a function of your curiosity, cultural and social assumptions. Right, like if you're investigating something having to do with operating a motor vehicle, start with age ranges that include where people start to learn to operate motor vehicles, right, or are legally allowed to in their communities. Let's see, 1, 2, okay, cool. So we've got some high income, low spenders. This is what we found, and we've got some low income, low spenders. How does gender play into this? So this next scatter plot is income by spending score. So we have our general, that X again, and our data is folks under 40, and I'm breaking out the hue, like is male or not, right? So that it appears it's possible that gender could make a difference here. We might just not have enough data points. Like we just don't have a heck of a lot of data points in the high earner, low spender. right? That seems kind of rare just based on the age range. Yeah. So you see how this is, these ask the question, answer the question visually or statistically, and then we write the conclusion. This is trying to exemplify that, that pattern that we've been trying to hammer home. Let's see, last little bit here. It's more than just a little bit. But what if we control for annual income? The spending score differ across age. Again, we do this because it's easier to read two-dimensional charts, multiple two-dimensional charts based on categories than like 3 4-dimensional things. So we'll create 3 bins of income, 0 to 40, 40 to 70, 70 to 140 bins of income. This allows us to plot out age and spending score, and we could set the hue by the bin. So we have three bins, 3 columns. Now this is really interesting, right? Income. Age is not accounted for here because this is all of train. I'm sorry, age is totally accounted for. Age is the x-axis. So what we're doing with these interplays is if we have a categorical that we want to control for, we turn it into a set of bins. And then we view the other pieces of data through those 3 bins. So right now we are viewing all of age, all of spending score through the 3 bins of income rather. So we have 0 to 40, 40 to 70K, and 70K up. And this is really interesting. So we're like, where is the orange? Across all age ranges. Orange is kind of medium spending scores. That's really interesting. And that's kind of, I mean, these bins are kind of large, but that just leaps off the screen, doesn't it? Yeah.
Possible that, let's say, the more data you have in certain regions, because I kind of believe that a lot of people are between 40 and 70,000, like pretty much. So could it be like the more data you have at a specific point, the more kind of relationship you can see,
The more,
of a relationship you can see. Because like right now we're observing this here, and I feel like a lot more people are in between 40 and 70,000
rather than a percentage of what's,
household.
yeah. So looking at this, these all look kind of equal, just visually. There's as many green points as blue as orange, give or take, right? But in what I'm hearing you say is in reality, folks earning 40 to 70, there's a lot more individuals as a proportion of the population. Is that what you're saying? Yeah, I agree with you. In this data set, they appear to be roughly similar. Yeah, but how would this look? Like if this was more representative and we had more individuals, the middle orange bar would be thicker, right? Bert?
So this kind of information, we come to the conclusion as to like, we go for the middle class versus an age group. Is that what we get from this in a sense?
Oh yeah, the orange here?
Yeah. So
Yeah,
if you're
moderate.
like sales, you target more of like the middle class versus an age group. I get that information out of it.
Yeah. Yeah, you could make that argument from this. Yeah, I think so. This is saying moderate, I mean, middle spending at all ages in this income range. That's a nice steady customer, right? Yeah. Pete, something to add?
When you say control for a better variable, you mean like split it so it's a little bit more versatile?
A little bit more.
Noticeable?
Yes, that's exactly what I mean. Right? If we have, say we have X and Y for, let's just control for gender, right? So X and Y, and we have a relationship that's like, whoop, for males. And what if we have a relationship that's whoop, for non-males? We just controlled for gender. And if we You could plot these on two different plots. You could plot them on the same thing, use different colors for them. It's really more of like mentally controlling for, because the code will do whatever you tell it to do, right? And if those two lines have the same shape, then this tells us that gender isn't an explanatory reason for the relationship between X and Y. For smoking status or whatever else, yeah. Cool. So this type of exploration, folks, is not specific for clustering exploration, but this is very valuable just in your toolbox because we are having, I mean, anytime you can get 3 variables on the screen and they make sense, that helps. Anytime you can get 4 variables on the screen and they make sense, that's okay too. It's the making sense that's the hard part. Pair plots can take a very long time to run. If you don't believe me, the curriculum says long with 1, 2, 3, 4, 5, 6 ends. So that's very long. This is exceedingly processor intensive if you have 2 million data points or 70,000 data points. Y'all know this already. What's really cool, we can try to control for certain variables by using the hue argument. So hue can accept a categorical or a numeric argument. I prefer categorical stuff because the colors are more clear. Like if you can feed in a continuous value to hue, but if you're colorblind like myself, that you just lose a lot of data that way. And your colorblind audience will lose a lot of data that way as well. There'll be lots of peaches and pastels and lavenders and everything, and it's easy to miss the forest for the trees. Cool. So let's take a peek at the exercise. We don't have a specific like 1A, do this, 2B, do this. But ask at least 5 questions of your data. If you want a hint on what to ask something you haven't asked of your Zillow data before, right? We've got some other hints in the exercise, in the curriculum here. Keep in mind that for the new project, your target variable is now log error. It might be helpful to explain what the heck log error is for us. So have y'all noticed that you get tax information on the Zillow data set, but you don't actually get Zillow's prediction? That's because Zillow ain't gonna give it to you, right? They don't want, they certainly don't want us to figure out their algorithm, right? That's protected. Even if this is 5 years old, they still don't want us to figure it out. But what they are providing is this thing called the log error, which is, let's see. Folks at home, do y'all see my editor in front of me?
No.
No? Okay. Cool. Just to cover this real quick. So we have received and calculated errors before. That's like, oh no, there's no Y hat there. Y hat minus Y is one way to get an error, right? So you take the prediction of a value minus the actual value. Well, what's going on with Zillow's log error is it's taking the log of Y hat minus the log of Y, which is the same thing as the log of the error. So why is this interesting? Zillow put up $1.5 million as a purse prize in 2017 for this challenge here. Now, the goal with regression is to get your error really low, right? Well, how can you get your error really low? A couple of ways of getting your error really low is having a good model. That's one way. Another way of getting your error really low is being able to predict error on its own and use that as a feedback, basically to juice your algorithms. The methods for doing that These are called boosting algorithms. I'm not going to go into boosting algorithms right now. But the punchline is, if you can get really good at predicting error, you can make better models with less error. Why? Because if you figure out what's driving some variable, you can figure out what's, I shudder to use the word cause, but what's related to that variable. So this is what Zillow did, and it's really ingenious. They said, hey, everybody, they actually have the real sales price for things that changed hands in the past. So they have Y, and they had what their prediction of the market was at that time. So they had Y hat, and they're giving us log error. So that log error column, it is just a number, right? But think of a second order effect. If you're good at predicting error, then you can make algorithms that you learn from reducing the error to make a better overall model. Out of scope for this one thing. Yes, there is more to data science than just what we cover in Kodak, right? Yeah.
Is there a specific reason why they're using a log here instead of here, just to make it smaller?
Probably because of the exponential nature of house values. Like this would lead me to believe that there is some sort of logarithmic relationship. They wouldn't log transform if that produced more error. But it's probably just because it's an exponential.
That there's some sort of growth of the error as it goes up.
Yeah. Well, I think we saw that with a number of people's projects. The predictors were predicting too expensive for cheap properties and much too cheap for expensive properties, right? So I'd be willing to bet that their decision to take the log of that has to do with errors getting higher the further away from an inaccurate prediction you get. Yeah. So it is a new term, this log error, but it's just a number. You're just doing regression on a number.
Is there a certain type of, I'd say, like machine learning algorithm where it just log values, like I don't know how to call it, log values kind of work better, like time series or something like that, or?
Not magically, not automatically, but
Because I assume like this can go back years and years.
the data itself has to establish that relationship for that transformation to be valuable. But like the natural log is very, very useful with things like rainfall and hours of sunshine. A lot of physical systems do well with the natural log transformations, and a lot of exponential systems, human activity exponential systems generally do well with log-based 10. But it depends on the data, the underlying data itself. Yeah. Like if you've got, I'll go on a little bit of an aside. Just for some brain food. God, I don't know. Something that is distributed kind of like that. Whatever your x is, you might take the log of x and see, and they end up, if this is a natural log, it may end up being a straight line or something approximating a straight line. Depends on the underlying data. It depends. There's your data science answer. Cool. So remember, the thing that we're trying, that little aside on log error, was because the exercises say, hey, don't forget your target variable is log error. Any work that you do on this turns into work on your project. So this is really useful time. And then we've got a bonus there, should you feel so brave and bold. If you wanted to explore actually, we'll be using the mall data for modeling and using clusters. So just use this time to get to know Zillow. And then we'll have a little bit of time for demos in the morning, like hopefully more than 2. but not like 20. That would be too much. Like 5 demos would be nice.